Hello and welcome to College Physics 2, Lecture 12, EMF, Resistance, and Ohm's Law. To begin, we will have a discussion about batteries and how they actually work. A lot of times with this material, as we've discussed in the past, it's often hard to visualize what's actually happening, and so as often as we can, we like to make analogies to better understand the internal processes that are occurring at all times in the batteries, in our wires, and other circuit components. To start with this discussion of a battery, we're going to immediately hop into one of those analogies. And in this case, it's going to be an analogy of an escalator of some sort. So we say that a battery acts like a charge escalator. In other words, it takes charges from the bottom, or the, say, negative terminal of the battery, and lifts them up like an escalator to the top of the battery, or the positive terminal of the battery. What's occurring here is we're seeing the charges being lifted from our zero potential negative terminal. Remember, in our past, we said that, much like the ground is your 0 point for gravitational potential energy, the negative terminal or negative plate of the battery is our 0 point for potential. So as the charges are lifted up higher and higher and higher, it's sort of like lifting them up that waterfall analogy we talked about in the past. They're moving further up, so it's sort of like just taking an object and lifting it up physically to a higher point. In other words, you're gaining potential energy. In this case, it's not, physically being moved upward, it's just, a hypothetical, right? They are gaining electrical potential energy in this case. So the whole point of a battery is to use its chemicals inside to give your charges that potential energy up at the positive terminal of the battery. Well, once this happens, we can then sustain current in a circuit. Well, we do this by basically thinking of that waterfall analogy again. Once we're at the positive terminal of the battery, the charges move through the wire, fall back down to the zero potential or negative terminal of the battery, and then it starts all over again. The way I like to think of this is to consider one of those like desktop or outdoor water fountains that have waterfalls in them. You have a water pump that pushes the water back up higher so that it can fall down the waterfall. And that's exactly what's happening here, just with charges, essentially. So anytime you have a battery driving current through some closed loop, it could just be a simple wire like you see in this picture, or a wire consisting of multiple other components, we consider that complete loop called a circuit. So we say it's a complete circuit. So again, there's a lot of analogies to consider, but basically think of the battery as a pump or an escalator, lifting your charges up to the top so that they can fall back down and repeat the process until the battery runs out of its chemicals. Now, we don't really go into the details of what's actually happening inside of a battery because it's beyond the scope of this course. We can kind of just give a general view of it though. And so I figured I'd throw this in to the lecture. This isn't particularly necessary for my actual students, but I think it's at least good to kind of know what's going on. So obviously we need power to drive this whole process, right? This has to be coming from somewhere. You can't just create energy out of nowhere. So the way a battery works is it uses chemicals inside of it, which we call electrolytes, that are sandwiched between the anode and the cathode, so basically the positive and the negative terminal. Those chemical reactions inside are going to separate charges, right? Actively separate them, positive and negative, by moving them to one of the electrodes or the other. And so these chemical reactions keep going over and over and over again, or continuously, until it runs out, right? So until that supply of chemicals is depleted. When that happens, your battery is considered dead, and then without a supply of charge anymore, your current in your circuit shuts down, and so if it's a flashlight, let's say, your flashlight no longer turns on because there's no chemicals driving that process anymore. Obviously, there's a lot more intricacies to all of this, but that's your basic view for now. Well, we are going to make one new definition here, and this is one that I always thought was kind of odd, It's one that I didn't well understand when I was a student as well. But when you separate charges, by definition, you establish a potential difference. We talked about this several lectures ago, but if you actively separate charge, that is what causes the potential difference. Well, that's what batteries do. They separate charge with those chemicals. And so that is what's establishing the potential difference of your battery. So if you say you have a 9-volt battery, that is caused by charge separation on the inside. Well, anytime you have a device that actively separates charge to give itself a potential difference, we call that potential difference the EMF, epsilon. EMF stands for electromotive force. So even though it is still a potential difference, say 9 volts, we call it the EMF if it's coming from something that separates charge. So I just keep repeating myself on purpose for this, but it's so hard to get this term confused, especially because it introduces a new Greek symbol and it's an abbreviation, EMF. It's scarier than it is. So just remember, it's literally potential difference. In other words, it's still measured in volts, V, and so, it's the same thing. It's just applied to batteries, basically. So, for example, something that doesn't have an EMF would be a capacitor. Capacitors can store charge. You can have some charge on the positive plate and some charge on the negative plate. But the capacitor itself doesn't do that separation. So because it's not separating charge, we don't say it has an EMF. It just has a regular potential difference. So I know this is a technicality, and it's not severely important for a basic course like this, but we will be using the EMF in place of potential difference throughout the upcoming several lectures. So just something to keep your mind on. So altogether, we're going to start learning about something that is kind of dictating how current is going to flow through our circuits. And there are several factors that determine what current you're going to get through a circuit. It's not just how much power you have or how big of a battery you have, although that is our first point here. The potential difference will certainly dictate how much current you have, because a larger potential difference will create a larger electric field that can push the charges even harder or faster through the wire. In other words, giving you a larger current. So a good example of this, like you can see in the top right, if you connect one battery, sure, you'll get some current flowing through, but what if you connect 2 batteries together? Well, now you've got double the potential difference, and so you have more current flowing through your wire. Another factor is the dimensions of the wire, and this one can be surprising to some people at times, but I'll try to make it a little clearer just with some basic descriptions. The easier one, I think, to understand is having a thicker wire would allow for a greater current. So basically, it allows more charges to flow. The way I kind of think about it is it's like adding an extra lane or two to a highway. You can fit more cars down the road if you have more lanes. And so that's kind of what's happening here. You have more room for the current or for the charges to flow as a current. So thicker wires means more current. On the other hand, longer wires have the opposite effect. It will decrease the current. The way I think about this one is it's just basically friction. The longer your wire is, the more stuff that your charges have to bump into. And so they're going to slow down to some degree and have more resistance, which is a term we haven't used yet, but resistance to flowing. And so longer wires mean a smaller current. And then the last one. The material from which your wires are made will certainly play a difference. Right? I mean, there's a reason why most of our wires are made out of copper and not any other substance, right? So think about that, right? I mean, there's a reason why we're building our wires with copper. So the material in which you're using will matter. And it's really a measure of conductivity. How conductive is your material? Is it really conductive, in other words, allows charges to flow easily? Or is it a better insulator, which wouldn't allow charges to flow efficiently, which means it'd be foolish to make a wire out of it? So all of these factors come into play when you talk about resistance. Resistance, which we represent with the symbol R, is a measure of how hard it is for charges to flow through a wire. The more resistance you have, the harder it is for the charges to move. So this isn't a term that only applies to charges. You've heard the word resistance before, of course. So thankfully, at least this term is straightforward. Now, the current that you're going to get in your wire will depend both on that resistance, because, again, more resistance means it's harder for your charges to flow, and the potential difference, which we just talked about on the previous slide. We said a potential difference, if you increase it, you'll have a harder push on your charges, so more current. So overall, the idea is that in terms of resistance, or current, or whatever, there's an equation that relates all three of these quantities: potential difference, current, and resistance. And that is known as Ohm's law, which is most commonly written as delta V equals I times R. In other words, potential difference is equal to your current times your resistance. To give you an idea, this is about as important as F equals ma was to our Physics 1 course. This equation basically governs a lot of what is happening in our circuits, and it's going to be used throughout the next several lectures. Basically through the whole third of this course where we talk about current. So this is basically, in terms of importance, the F equals ma of this class. Now notice we introduced a new term, resistance. Anytime you have a new quantity, we have a new unit to describe it. So looking at the equation, I wrote it here off on the side. Looking at this equation, we have delta V over I for resistance. Well, delta V is measured in volts, and current is measured in amps. So the units of resistance is a volt per amp. But we give that a new name, and that is the ohm, or omega symbol the omega symbol is what we use to represent that. So the standard unit for resistance is ohms, which is a volt per meter. Well, that's not the only way to describe resistance, because if you go back to this discussion, nowhere in our Ohm's law equation does it consider the dimensions of the wire or what the material is made out of. So that hasn't even come up in our math yet. So we need a way to describe the resistance of a wire based on those properties. And that's where the quantity known as resistivity comes into play. Resistivity, represented by the symbol rho, that's the lowercase Greek letter rho, I call it curly p, that characterizes those properties of the materials, in other words, what they're made out of. And the units for this are ohm meters. So resistivity is just the way we describe what the material is made out of. If you have a material that is a very good conductor that allows charges to flow easily, it has a low resistivity. But if your material doesn't allow charges to flow easily, in other words, it's a good insulator, that would have a high resistivity. On the right-hand side, you see a table of resistivity values for all sorts of different materials. As a disclaimer for my students, I do not make you memorize these. I think that would be mean, to say the least. So you're given this table as a reference here in your notes, or also I put this on the exam in case you ever need it. So do not worry about memorizing these values. So notice copper, which we make basically all of our wires out of, is right at the top here with the smallest resistivity value out of everything listed. In other words, copper allows charges to flow very efficiently, and so that's why we make our wires out of it. So if we want to figure out the resistance of a wire, how much is going to resist current, it depends on this resistivity, how long the wire is, as we talked about, and how thick it is. In other words, the cross-section area A. So all of those quantities together dictate your resistance by the formula shown at the bottom. Resistance is equal to rho L over A. In other words, the resistivity times the length of your wire divided by its cross-section area. So let's go ahead and hop right into an example using this equation so we can fully understand it. There is one thing I meant to include here, but the problem says we have a 60-watt light bulb with a resistance of 240 ohms. if the wire used to make the filament in the light bulb is 0.04 millimeters in diameter and made out of tungsten, how long must the filament be? Now note, the one thing I wanted to mention is that on your table, there are two values for tungsten. One at room temperature, and the other one basically when your light bulb is turned on. So for this particular problem, we're going to be focused on when the bulb is turned on, so we're going to look at the higher temperature value. Students, if I ever give you a problem like this, I will be more specific. If you need to use tungsten, I will tell you, if the bulb is turned on or not, or what temperature to use. With that out of the way, let's go ahead and try to solve this problem. We're looking for the length of the filament inside the light bulb. So we know we're going to be applying our equation, resistance is equal to rho L over A. Because that's the only place where length shows up. So if we're solving for length, L, we need to rearrange our expression. Multiply A to the other side to give you RA. And then you have rho that you need to divide by. So some basic algebra, and we see that the length of the wire will be expressed as the resistance times the cross-section area divided by the resistivity. Now note, we are given the resistance and we're given the diameter, but we're not necessarily given the cross-section area. So I'm going to just go ahead and plug that straight into my equation. We can say it's resistance times the area, which would be pi r squared. Right? The area of a wire, wires are round in nature, or they're cylindrical, but I mean if you cross-section that wire and look at it from the end on, it looks like a circle. So the area is pi r squared. So we can go ahead and try to plug in our values and solve at this point, because we do know the resistance, we do know the radius, and we do know our value for rho. The resistance was given as 240 ohms. I will mention every time I draw the ohm symbol, it's going to look different. I'm bad at drawing the ohm symbol. Anyways, then times pi times r, the radius, which is half the diameter. So if we have 0.04 millimeters in diameter, that means 0.02 millimeter equals the radius. But again, keep in mind, that's millimeters. We need this in meters. So I'm going to write this in scientific notation. It'll be 2 times 10 to the minus 5. 2 times 10 to the minus 5 meters, quantity squared. Right, because a millimeter is 1/1000th of a meter. So we have to take our decimal place, move it over 2 times, but then move it over 3 more times for the millimeters to meters. So that's moving over 1, 2, 3, 4, 5 spaces. So that's where the power of minus 5 came from. Now, from our table, the value for rho at 1500 degrees Celsius is 5 times 10 to the minus 7. So 5 times 10 to the minus 7, and again, ohm meters. Well, plugging this in, we should get a length, which can be surprising, of 0.6 meters. So, 2 things to note once we have our answer. First, it told us it was a 60-watt light bulb. That number is irrelevant. We didn't use it, we didn't need it. Second, that length is surprising perhaps, right? Because 0.6 meters, that's about 2/3 of a meter. Well, a meter's about 3 feet. So what this is telling us is that the filament in a standard light bulb is about 2 feet long. So that can be surprising, right? That's about 2 feet. So inside of the light bulb over here, that filament that's coiled around twice, notice that it's coiled around in a small little coil, and then that coil itself is spun around in a coil in the middle. Well, it's like that so we can fit such a long wire inside, a long filament. Because remember, the longer the wire is, the more resistance there is. Well, that's the whole point of a light bulb. You want to resist the current enough to make it get hot enough to glow and give off light. So the longer your wire is, the more resistance there is, the brighter your light bulb can get. So that's why we try to pack as much of the filament into the light bulb as possible. And if you uncoiled that, it would be about 2 feet long. So I just thought that was really fascinating. Okay. To conclude, let's just do one quick check, or one little end of lecture question. This one involves a little bit of math processing, so I'm just going to go right through this one with you all together. So this problem says wire 2 is twice the length and twice the diameter of wire 1. What is the ratio of resistance 2 divided by resistance 1? So let's just go ahead and solve this together. It does involve some math. You can probably do it mentally, but it's not easy. So we have the equation for resistance as rho L over A. But remember, we said area for this type of wire is a circle. So the area of a circle is pi r squared. At this point, think about what we're doing. In the second wire, we double the length, and we, this is like, say, R1, and then we double the radius as well. So that's like plugging in a 2 times L up top, because we're doubling the length, and 2 times the radius, right, for the second wire. So we have a factor of 2 up on top, but here we have a factor of 2 quantity squared. So that's 4. So this is basically a factor of 2/4 times the original equation. In other words, that's 1/2. Right, so we have half the resistance. So our answer here is B. All right, so it's just a little bit of ratios. We don't do a lot of these types of problems in my course, so that's why I just wanted to work through this one with you together so you can kind of see how this process would work. That's the only one for this lecture, so that is a great point to leave it. This is the end of our lecture here, but we're going to go into the concept of actual resistors and talk about energy and power in our circuits in our next lecture. As always, thanks for watching, and have a great day.